In the last lecture, if you remember, we established this for a one-dimensional element, which was like this, and we established how the stiffness matrix of one-dimensional element will look like. Now we will try to solve a problem today, a very small one, and then we will proceed with that. So let us look at a bar which is fixed from both sides. Okay, so this one is fixed from both sides, and although it looks like a uniform bar, we are going to have some differences which we will discuss, but we will not show in the diagram. Okay, so let us divide this thing in three elements. Okay, we have E1, E2 and E3, and the area of the first element is, let us say, 6. It can have, so let us write there, so 6 millimeters square, and then area here is 8 millimeters square, and area here is 9 millimeters squared. Okay, and the elastic modulus also differs. So elastic modulus is 200 gigapascal there and 300 gigapascal here, and again 200 gigapascal here. Okay, so this is how it is, and now let us look at that. What are the how we are going to find out the forces, and how are we going to find out the displacement values, and the length here. So this length is, let us say, L1 is 120 millimeters, and this length here is also 120, and this length here is 180. Okay, so these are the three different lengths: area, elastic moduli, and now also apply some forces. So let us apply a force here, and this force is, let's say, 300 newtons, and here let us apply a force, and that is minus 125 newtons. Okay, so this is our problem, and now let us try to solve it one by one. So now let us look at the stiffness matrix for element number 1. We usually have the same thing, so it is AE by L, 1 minus 1 minus 1 1, because this is general. This is true for any bar. Okay, any one-dimensional bar, this is going to be the stiffness matrix. Okay, so elementally we can solve the problems. Okay, so elementally we can write that F1 and F2 is equal to A. So what is A here? So A is 6, E is 200, and length is 120. So A is 6 millimeters square, E is 200, so 200 gigapascal is 200,000, megapascal is 200,000 Newton per millimeter square. So 200,000 newtons per millimeter squared, and then we have a length of 120 millimeters. So millimeter squared got cancelled, and then we have Newton per meter. Sorry, Newton per millimeter. Newton per millimeter, and then we have a displacement applied which will be in millimeters, so that will cancel out. So we will have force in Newton, so we are okay with that dimensionality. So this will be AE by L will be common for both, and then I will have 1 minus 1 minus 1 1 into D1 and D2. Okay, so D1 and D2 are unknowns. F1 and F2 we know. So there will be reaction force on node number 1, and there is a force on node number 2. Okay, so on node number 1 we have a reaction force F1, and node number 2 we have a force which is 300 newtons, and this is going to be equal to, so this is 1200,000 divided by, so I can cancel some things out here. So 2 and 10, so this is this is 1000. No, this is 10,000. So this is 10 to the power 4, and then I have 1 minus 1 minus 1 1, and d1 and d2s are not known to me. So I have 2 equations and 3 unknowns. Okay, and therefore this is not going to work out, but never mind. So this is for the first element. Now let us look at, so this is for element number 1. Okay, this thing is for element number 1. Now let us look at element number 2. I have again f1 and f2, right? And here I have on f, so f1 is actually f2 and this is f3. Okay, because if you look at this element, then this node is 2, this, so let me do the node numbering also. So node number 1, node number 2, node number 3, node number 4. Okay, so at node number 2 I have f2 f3, and then again I have, no, but here AE by L is different. So here I have A is equal to 8 and E is 300. So I will have AE by L, so 8 into 300, 10 to the power 3 divided by 120, and that's it. Okay, so 1 minus 1 minus 1 1, d1 and d2. Oh, here I know d1, so d1 is 0 because there cannot be any displacement here, so d1 is 0. So I have one unknown and second unknown and 2 equations, so this is solvable. Okay, here I have d1 and d2 unknown, right? But f2 and f3 are known to me. So f2 is 300 newtons and f3 is minus 125 newtons, is equal to 8 into 300 into, but you shouldn't solve it individually in each element because the forces are distributed in 2 different elements, and this is why we need to assemble it, and we will do the assembly. So here it becomes what? So this becomes 240 divided by 12, so that becomes 20. So this becomes 2 into 10 to the power 4, 1 minus 1 minus 1 1, and d1 and d2 are, so this is actually d2 and d3, and that is for element number 2. Now let us do it for element number 3. So element number 3, I will have f3 and f4, and f3 is minus 125 and f4 I do not know what it is. So f4 is an unknown, and then here what is, so my value of area is 9 millimeters squared, and my elastic modulus is 200 gigapascal, and the length is 180. Yeah, so AE by L 10 to the power 3, and then 1 minus 1 minus 1 1, and then I have D3 and D4. D3 is not known to me, D4 is 0. Okay, so now I have minus 125 and F4 equals, so this becomes 20, this becomes 10, so this is 10 to the power 4, 1 minus 1 minus 1 1, D3 and 0. Okay, so this is my element number 3. Now we will assemble these things. Okay, so now we will assemble these. And how do we assemble it? So let us make the assembly matrix, and in this assembly matrix let us divide that. So how many degrees of freedom do we have? We have, so if we look at the problem, we have one number of node here, 2, 3 and 4. Okay, so we have displacement 1, 2, 3, 4, so we have 4 degrees of freedom. So we should have 4 by 4 matrix. Okay, the stiffness matrix should be 4 by 4, and we will make that kind of matrix. So Now, so in order to do that, a simple thing what I can do is I can divide it into 4 rows and 4 columns. So 1, 2, 3, 4 and 1, 2, 3, 4. Okay, and let me name these. So I will name these as degrees of freedom. So 1, 2, 3, 4, and then here I have 1, 2, 3 and 4. Okay, and now I will just put it simply. So what should I put? So this, if I look at it, this is K11. Yeah, this is the house of K11. And then I have K12, right? 1, 2. I don't have K13 and K14. Now I have K21, so 2 and 1. Sorry, 2 and 1 will come here, right? So K11, K12, and then K21 will come here. Okay. So this is I and this is J. Okay. So K21 will come here. Then K22, oh. No, this is wrong. So K2, oh. So K21 will be here. And then this will be K22, right? And then K31, well, you can actually populate all those. So K11, K12, and then K13, K14, K23, K24, K31, K32, K33, K34, and so on. So K41, K42, K43, and K44. Okay. So these are the components of this stiffness matrix, and not all of them are available. So now let us look at the element number 1, and element number 1 is here. So I have K11, K12, K21, K22. Okay. So let us populate this part. So let us put element number 1 where it belongs. Okay. So element number 1, I have 10 to the power 4, 1 minus 1 minus 1, 1. That is my stiffness matrix. 10 to the power 4, 1 minus 1 minus 1, 1. Okay. So element number 1 will have component K11, K12, K21, K22. Okay. So that is 10 to the power 4, and then minus 10 to the power 4, and then minus 10 to the power 4, and then 10 to the power 4. Right. So 1 minus 1 minus 1, 1. This is because of element number 1. Then element number 2 will have components like K. So I will have Kij. So I will have K23, then K24. No, this is confusing. So let me just see again. So I will have, where is it? Yeah. So I will have K11 because that is because of the node number 2 on node number 1. So first component is Kij, where because of J, the displacement at J, you are feeling the force at I. Okay. So in element number 2, I have node number 2 and 3. So first component will be because of the displacement at node number 2 on node number 2. So K22, then on 3, sorry, because of 3 at node number 2, and then I will have at node number 3, because of displacement at node number 2, and so on. So these will be components of element number 2. So let me put it here somewhere. So what are the values of element number 2? Element number 2, the values are 2 into 10 to the power 4 and 1 minus 1 minus 1 1. 2 into 10 to the power 4. Okay. So first component is K22. K22 is here. I already have a value because of the first element. So what do I do with this? I simply add it. Okay. So I will simply add the contribution coming from the second element. Why this is happening? Because this is the node which is being shared between two elements. So this is the node which is being shared in this element and this element. So this node will have contribution coming from both the elements. Okay. So I will have to put here the second contribution, 2 into 10 to the power 4, and then 2 3 is minus 2 into 10 to the power 4, minus 2 into 10 to the power 4, and 2 into 10 to the power 4. Okay. So now I have elements because of element number 2, and now let us look at element number 3. So if you see element number 3, then I have node number 3 and node number 4. So components will be here the stiffness because of the displacement applied on node number 3 on node number 3. So K33. Then on node number 3 because of the displacement at node number 4. And then on node number 4 because of the displacement, so on node number 4 because of the displacement at node number 3 because of the displacement at node number 4. So these are the components from element number 3, and let me populate this. So what are the values? So I have 10 to the power 4, 1 minus 1 minus 1 1. So again K33 is shared because this node is shared between this element and this element. So I will just add it here. So I'll put K33, which is 10 to the power 4 minus 10 to the power 4, then minus 10 to the power 4 and 10 to the power 4. Okay. So this is all I have, and rest of the things will be 0. 0 0 0 0 0 0. Okay. And these number of zeros, they actually become very large in a big problem. Okay. So if I have, let us say, 100 number of elements in one dimension, so I will have to make K matrix, which is 100 cross 100. Okay. So I will have 10 to the power 4 number of components in it, elements in it, not finite time. So these boxes, so I will have 10 to the power 4 boxes in it, and many of these boxes will have no value, so they will have 0 value. Okay. And when you code it, when you write a program to run finite element analysis, then this is a big problem. Even though we have not yet gone into plasticity, we have not yet gone into any other complications. This is just linear elastic calculation. And here you have problem because you have to create a matrix which should have these many components. And out of these many components, many of the components are 0. They don't have any value there. But even if they don't have any value, you have to create the space for that, right? So for instance, you create an array. Okay. So you will assign a size of the array to this, right? So that will be 100 cross 100. And once you create this space, the RAM is consumed because that much amount of memory has been allocated and defined for this array, or if you are creating a matrix in MATLAB, then for that. If you are creating a pointer, then you also have a space assigned to it, although the pointer doesn't have any value for it. Okay. So that space has been consumed by the computer, and this creates a lot of computational issues because the problem unnecessarily consumes a lot of RAM, and then you need a bigger machine to do it. But this is unnecessary. So what people do is they use a sparse matrix. Okay. Sparse matrix in MATLAB, you simply write sparse matrix. I don't remember the syntax for that, but I think in many of the programming languages you can create a sparse matrix, And a sparse matrix is simply what it means is that sparse means vacant kind of, so porous. It means in the literal meaning of this word is, and so if you create a sparse matrix, what you do is you actually define the values only for those places where you have values. So you say I, j, and then you write the value, whatever it is. So tell the number of I and j and 10 to the power. So the values for that you can simply put comma and put the values for that. And that's how you create a sparse matrix. So although it is cumbersome to write a sparse matrix, but the space problem will be decreased. So you will not create any space for this. Okay. But don't do something like this, that don't create an array of 100 and 100 size and then say that only these elements are there. Okay, because if you do this, you have again created a space. So right away from the very beginning you have to create a sparse matrix. Okay, you cannot create a matrix and then make some of the elements null. That will not solve the problem, because at least for one time you will be creating that space even though you are deleting it afterwards. Okay, so that is not as beneficial as creating the sparse matrix from the very beginning. Okay, fine. So that was the code perspective of it. Now we have assembled the whole stiffness matrix, and let us bring this stiffness matrix to find out the real solution. So now we have forces. We have forces F1, F2, F3, F4. Okay. And this is equal to the stiffness matrix which we have created. And what is that stiffness matrix? So we have 10 to the power 4 minus 10 to the power 4, 0, 0, 10 to the power 4 minus 10 to the power 4, 0, 0. Then we have minus 10 to the power 4, and I think this will be 3 into 10 to the power 4. So minus 10 to the power 4, 3 into 10 to the power 4. And then we have minus 2 into 10 to the power 4, 10 to the power 4, and 0. Yeah. So now it is not moving. And then I have 0, 0, 0, minus 2 into 10 to the power 4, 3 into 10 to the power 4. Okay. So 0, 0, 0, and minus 2 into 10 to the power 4, 3 into 10 to the power 4, 3 into 10 to the power 4, yeah, minus 2 into 10 to the power 4, 3 into 10 to the power 4, minus 10 to the power 4, then symmetric, then 10 to the power 4, okay, so minus 10 to the power 4, symmetric, 10 to the power 4. So this is my stiffness matrix, and then I have displacement values. So D1 is 0, D2 is D2, D3 is D3, and D4 is 0, okay, and then I have F1 is 0. Oh, F1 is not known. F2 is 300. F3 is minus 125, and F4 is not known. So this is my problem, and this is what I have to solve. Okay, and so this equation will be solved by certain technique. By the computer, and once you have solved it, and then you will have the values of F1 and F4 and D2 and D3. Okay, so usually you can do Gauss elimination to find out the values, or you can simply try inverses. So for instance, if you do not know any of the values of forces, so let us assume a situation where we do not know the values of F2, F3, F4. So we don't know all this, but we know the values here. Okay, so we have minus 0.02, and minus 0.02 will be compressive. So let us put it 0.1, and then minus 0.2. But the stiffness of the second bar is higher. Yeah. So if there is a displacement of 0.1 here, then you should have less, so that will cause a force, and that will cause a force, and that amount of force will not be able to cause same amount of displacement because the stiffness is high. So you will have lesser amount of displacement into different direction. So therefore I should have 0.2 here and 0.1 here. Okay. So let us say this is the situation. So if this is the situation, answer is straightforward, right? You know the values of F1, F2, F3, F4, just multiply these and you have the values. Okay. So right away straight answer. So then you will have the values of forces, you will have 10 to the power 4 into 0, then minus 10 to the power 4 into 0.2, then 0 and 0. So this is F1, and then F2 is this into this. So F2 is, so first term is going to be 0, second term is going to be 3 into 10 to the power 4 into 0.2, third term is going to be minus minus plus 2 into 10 to the power 4 into 0.1 and then 0. Third term is going to be 0 and then minus 2 into 0.2 into 10 to the power 4 plus 3, minus 3 into 10 to the power 4 into 0.1 and then 10 power 4 and 0 is 0. So that is okay. And oh, great. So talking about RAM consumption, this is what happens. And then F4 will be this into that. So 0, 0, these two are gone. Then only one term, so that will be minus minus plus 10 to the power 4 into 0.1. Okay. So these will be, so these are the straightforward answers for F1, F2, F3, F4. Now if, let us imagine a different situation where we know the force values. So we know the force here is, so first one, if that is being pulled by a force, right? So you will have a reaction force which is in the negative direction. So I will have minus, let us say, so the force which is being applied on node number 2 is minus, it's 300 Newton. Okay, so let us keep it minus 300. And then on node number 2 I have 300, but then there will be no displacement. So okay, so let us keep it minus 200. Minus 200, 300, minus 125, and on D4 I will have a reaction force in the positive direction, so let us say 100. Okay, so these are the forces, and then I have this stiffness matrix. And then I do not know the displacements, but D1 and D4 are known. So D1 is equal to 0, D4 is equal to 0, and D2 and D3 are not known to me. Okay, so if this is the situation, what will you do? If this is the situation, then in order to find out D1, D2, D3, D4, what you will have to do is, so D1, D2, D3 and D4 will be equal to K inverse and force vector, right? And this asks or demands that K1 has to be invertible. So K must have an inverse. If it doesn't have an inverse, if it is a singular matrix, then you don't have a solution here. And that will cause non-convergence, that will cause error in your finite element analysis. Okay, so how do you calculate? How do you know that it is invertible or not? How do you know that this is invertible or not, this matrix? So let us look at this matrix. So this matrix looks like this, okay? And how do we know that, how will you find out an inverse? So in order to find out an inverse, what you do is you do Gauss elimination, right? Or you do rows transfer, rows and column transfer by doing some multiplications, right? So that is the part of the linear algebra. So my intention would be to remove this element, to remove this element, and to remove this element, so that I make only upper triangular matrix, right? So in order to remove this one, what I will have to do is I will have to multiply the first row with certain number and then add it to the second row, right? This is what I will have to do, right? So if I do this, and then you keep an identity matrix next to it and keep on doing the same operation to that, and that's how you find out the inverse, right? So you will have to multiply this by 1, then add it, and this number will become 0, right? This number will become 0. Find what will happen to this one. So this one you are just adding it, so that means you have to subtract 10 to the power 4. So this will become, so let me take this matrix here. So now I will have to, can I copy this? Is this possible? Oh, not the whole thing. So this, okay, so this small format is good, but can I copy it? I think so. This is, no. Okay, yeah. So I copy this and I simply paste it here. Can I do that? Oh, I don't know what it has copied. So I want to copy this. Okay, leave it. So I'll just write it down. So 10 to the power 4 minus 10 to the power 4, 0, 0. Then I have minus 10 to the power 4, 3 into 10 to the power 4, minus 2 into 10 to the power. Let us keep 10 to the power 4 out of the picture. So let us keep 10 to the power 4 out. Then my matrix is 1, minus 1, 0, 0. And then minus 1, 3, minus 2, 0. Then 0, minus 2, 3, minus 1. Then 0, 0, minus 1, 1. This is my matrix. Okay, forget about this fellow. So if I have to remove this one, I simply multiply this by 1 and add it to the second row. Okay, so what happens then? So I have 1 minus 1, 0, 0. Then this becomes 0. This becomes, so 1 minus 1, 0. 3 minus 1, 2. Minus 2, 0. So that is unaltered. Okay, so now I have made my second row. So this element I have removed. Now I want to remove this one. Okay, I want to remove this one. So how do we do it? If I want to remove this one, I simply multiply this row with a factor of 2 and then subtract it, right? The factor of 2 and subtract it from this one. So, so that will cause something here. So I don't want to do it. So let me just write minus 2, 3, minus 1, 0, 0, minus 1, 1. And now let me operate on this. So now I want to remove this element. So I want to remove this element. So I'll just multiply this thing with 1 and add it again. So what will happen to my matrix? So I will have 1 minus 1, 0, 0. You see, you have to keep an identity matrix and keep on doing the same operation on that. Okay, so 1 minus 1, 0, 0, 0, 2, minus 2, 0. Then, and now I am multiplying this row with 1 factor of 1 and adding it. So factor of 1 adding it. So this remains 0, which is good for me. And then minus 2. And this will be minus 2 plus 2, so that will become 0. 3 minus 2 will become 1. Minus 1, 0 will remain minus 1. Then I have 0, 0, minus 1, 1. Now I will have to remove this one. So simply multiply this with 1 and add it. What will happen to my matrix? It will be 1 minus 1, 0, 0, 0, 2 minus 2, 0. 0, 0, 1 minus 1, and now 0 will remain 0, 1 minus 1 will become 0, and 1 minus 1 will become 0. Okay. Now it looks like there is a problem. So I have eliminated all the elements, but so now I have only upper triangular matrix. And here I can find out the determinants by simply multiplying the pivots. And the problem is here. This is the problem. So the determinant is 0. That means it is a singular matrix. That means the solution is not possible. Right? So this has happened because I have assumed some values. No, this has not happened. This has not happened because of that. There is no influence of these assumptions on the stiffness matrix. So this has become this is the problematic matrix because of our values of AE, A's and E's and L's. Yeah. Okay. So that is the process anyway. So this is an invertible, non-invertible matrix. It doesn't matter. It should be an invertible matrix. If it is non-invertible, if it is singular, it means that you will not have a solution. So that means there will be no convergence. Okay. So that's an error, but that's how you do it. That's how you find out the values of forces and displacements. Okay. The things are not so straightforward. So sometimes you have some values known here, sometimes you have some values known here, and you get a solution numerically from finite element analysis, and that's how you find out the force and displacement. For force and displacement, you calculate the strain. From strain, you calculate stress, and so on and so forth. So that's how we do it. In the next part, we will try to understand probably for two-dimensional elements, how do we perform the calculation for strain and stresses from the force and displacement. So for basically by solving F is equal to KU. Okay.